So here we will discuss about wave packet. The concept of wave packet comes in discussion of free particle wave function. So to start the discussion with wave packet, first we will start with free particle Schrödinger equation. So wave packet. I think everything is visible. Okay. So for free particle, Schrödinger equation is, there is no potential term, right? There will be only kinetic energy term. So psi is here wave function, and E is eigenvalue, energy eigenvalue. So now the solution of this equation. So first I will simplify the equation. Psi dx square minus k square psi, right? K is root over me by h cat. So the solution. Already we have solved various differential equations. So it is one kind of differential equations, and it gives this like solution. Actually, you may have learned about the solution consist with sine and cosine, but here I am writing, you can see, with exponential term. We can express sine and cos in terms of exponential I something, I theta. So that thing actually I have simplified that. So now, if I take into consider the standard time dependence. So taking the standard time dependence, that is it is exponential I e t by h cat. So the time dependent Schrödinger equation. Now here you can see psi is a function of spatial coordinate and also time. So it will be like exponential I k x minus h cut k 2m t. V exponential minus I k x plus h cut k 2m t. Then I have converted E is E term into K and put it here. So now if I simplify. Now here one thing you have to understand that you already know the plane wave equation, that it comes into like something with you can, if you remember, it comes like something like Ax plus minus Vt, right? So if I simplify this or represent this equation in that of plane wave equation, suppose I can write I think this is like that, V T, okay, T. Suppose I am now naming it quantum, plus V exponential minus I k x plus p t. Now here from these two terms you can easily understand that this first part actually represent wave moving towards left side, and it is moving towards right side, right? Am I right? Or it is different, you see. Okay, whatever is. So one is for left moving and other one is for right moving. So I can generalize this equation simply. So in the wave function, just I will keep one coefficient. I can keep one coefficient and define k in such a way that it is I kx minus h. I am bringing k inside the bracket. Okay, so it is like that. So now I will set some condition on k so that it will satisfy this equation. So plus minus root over 2 h bar. Okay. So with what are the condition? K is greater than 0. So k is greater than 0, then it is traveling to right. So previously I was wrong that this equation represent traveling to right side. Okay, and this equation represent traveling to right side. So if k is greater than 0, then this represent traveling to right side and traveling to left. Okay. So I think you have already understood all those things. Now, so from this plane wave, you can see we can extract the velocity. Now you can see from this argument. From this argument, we get one kind of velocity, and I call it quantum, V quantum. Okay. So what is that? This is V quantum is actually h got k by 12. If I convert it into energy, and you know that h got is p. You know p is h got k momentum. So in energy term, easily it can be converted into like that. And also from the energy, actually from the energy, that is we know that in kinetic energy equals to, here is only energy, kinetic energy, because it is free particle. Potential energy is 0. So from that part, that is equals to half mv square, we get V classical. I name it V classical. It is you know the form already you have done several times like this. So from that you can see that it is actually 2 to 4 2, so 2 VQ. You can check it. So there you can see. So there is actually two types of velocity we get from this equation. So actually, what are the physical significance of those velocities? So already in wave and oscillation part, I think you have read that one velocity named phase velocity and other velocity named group velocity, right? So actually here also the same physics applies, and here it is just a minute. It is like a phase velocity, this one, and this is group velocity. Actually, this group velocity signifies the velocity of the particle, and that for which particle we are considering this wave function actually. So this one is the velocity of that particle. Okay, and this one is actually velocity of ripples, you can say. So now we'll come into the our main point, that what is actually wave packet. Why should we where this wave packet comes from. So this will now discuss. So suppose. Okay. So for that we need one thing from the previous semester or previous concept, that every wave function is actually normalizable, right? You know it. Every wave function is normalizable. So also it should this plane wave function, this free particle wave function should be also normalizable. So now if we normalize the wave function, you know the formula, procedure that we have to integrate for the whole space. This is psi, suppose this is k. So psi star first one, then psi k, dx. So these will come into, if you look at the wave function, okay, let me write the wave function here, it will be better for you. You know, psi x k, I'm naming it like that, a exponential I something, right? So now simply you will get a square, right? Integration. Now exponential I and its complex conjugate is exponential minus I, and you know that multiplication of the both will give 1. So only left with dx, and it is minus. So simply you can understand that this will give some some very high value, or either in another way I can say this calculation will blow up. So we can write this way. So that means that what we have discussed, we have formed a wave function of free particle. Is it the physically this wave function is not realizable? So no, that is not the case actually. Actually, this is actually a mathematical puzzle, you can say, mathematical paradox. So to solve this one, the concept of wave packet comes into action. So what is that? So scientists have defined the wave function in another way. You can see here, they have defined it 2 pi, okay, minus infinity to infinity, phi k. These one actually wave packet I am discussing actually what is the physical significance of that wave? H cut k squared 2m dk. Now you can see here I have used dk instead of dx. If you see the function, wave function, you can see that we have when you consider the function as function of x. Now here is the interesting thing, that now you are defining the wave function, and it is integration. Now if I look at the function, you can see here, okay. So the function is just a single wave function, but now you are considering some integration term, and also the integration is taking over momentum space. So for this, firstly you have to know the Fourier transform. So already in the last semester you have been taught the Fourier transformation. You will not just see what I am writing here. It is a very simple thing actually, not so hard thing. But you have to know the points. Now, what is actually Fourier transform and how it works actually. So now I will discuss a little bit about Fourier transformation. Transformation and momentum space. Momentum is wave function. Okay. So first I will define a wave function is time. I am writing time independent. Time dependent function. So it is 2 pi h cut. This is the definition. Okay. Now this is a constant term. Actually, this has been considered for the future reference. So if you have done some problems on Fourier transform, so you can understand why this type of constant have been taken, or and also in the later part of our calculations and also discussions, you will understand there is a significance of this constant. Actually, this is considered from the normalization factors. So now I am writing, suppose the function. Okay. So this is I x h cut. Okay. Now phi px dpx. So this is one function in the momentum space, and so in other way we can write this phi p term in terms of psi xt. This is a spatial coordinate. This is in a momentum coordinate, this psi xt, and we can define similarly phi px, this momentum function in the spatial coordinates. How we can write this one? Just same form, just a little bit tricky. Just you have to replace this plus sign with minus sign. Everything is almost similar. Sorry, the t term will be okay. So sorry, this is the x t, and you are performing using the x coordinate. So here you can understand. Now you can understand that why we have considered here dk, because this is in the momentum space, and this concept is coming from the Fourier transformation. Now, okay, this is clear. Okay, so in this way we can transform wave function into the momentum wave function. So firstly it was the wave function in the spatial coordinate, and then it is the wave function in momentum coordinate. Okay. Now this wave function. Now we can see that when we are considering this one, this means that this is the actually product of some wave function, multiple wave functions. That's why we are performing this integration. Just a minute. So what we are discussing is wave function. So wave function carries carries a range of k values. That means a range of energy and velocities. That's why we are performing integration on it. So now we can. So it is okay. So now we can write this wave packet form in terms of writing, right? From this Fourier transformation, you can write it is 2 pi. Okay. Infinity psi xt and Also, we can understand. We can write minus ITX because it is plus. You can see it is dx. Okay. So it is. Sorry. This is the case of time independent function. Because for time dependent there will be this term also. Okay, so this is the discussion for wave packet. So now we'll discuss the special case of some wave packet.